Welcome to The Explainer. Today, we are tackling one of the biggest, most critical decisions you can make in the world of AI, picking the right hardware. We're talking GPU versus TPU, and let me tell you, getting this choice right can be the difference between a massive breakthrough and a total budget bust. So why is this choice so important? Well, to get a sense of the scale we're dealing with, let's just start with a number that frankly sounds made up: 42.5 quintillion. That's how many operations a top-tier Google TPU pod can crank out per second. We are living in an era of compute power that was pure science fiction just a decade ago. And at this scale, specialized hardware isn't a luxury anymore. It is an absolute necessity. All right, so here's our game plan. First, we're going to cover why we even need these things called accelerators. Then, we'll break down the two key jobs in AI. After that, the main event, GPU versus TPU. We'll get into how to pick the right one for your job, see how you can deploy them on Google Cloud, and then we'll take a little peek into the future of this wild hardware arms race. So first up, the age of acceleration. You see, the problems we're trying to solve now, they're just too big, too complex for the traditional CPUs that have powered our computers for decades. We've hit a new frontier. And this new frontier is really dominated by two absolute giants: high-performance computing, or HPC, and of course the one you hear about every single day, artificial intelligence, AI. These two are the twin engines that are driving this insatiable demand for more and more powerful hardware. So what is HPC, really? Well, think of it as the world's most powerful calculator. It's what lets scientists simulate the climate, what lets engineers design revolutionary new airplanes, and what lets banks run incredibly complex models to figure out financial risk. It is all about tackling gigantic computational problems. And then, of course, there's AI. And this is all about teaching machines to think, to learn, and even to create. You know, from your phone understanding what you're saying to an AI model writing code for you. All of it relies on learning incredibly complex patterns from just massive amounts of data. And that task, it requires a totally different kind of horsepower. Now, inside the world of AI, there's this one fundamental split that changes everything when it comes to hardware, and that's the two sides of the AI coin: training versus inference. So first, you've got model training. Okay, this is the school phase. It is an unbelievably intense, power-hungry process. You're basically feeding a model a dataset, sometimes the size of the entire public internet, so it can learn. This is the heavy, heavy lifting, but the good news is you might only do it once for a particular version of your model. And then there's inference. This is when the model graduates and gets a real job. It's when you use that trained model to actually do something useful. Make a prediction, translate a sentence, generate a picture. This doesn't just happen once. It happens millions, maybe billions of times. And every single time, it needs to be fast and it needs to be cheap. So here's the bottom line, and this is really the key takeaway. Training is a marathon, inference is a series of sprints. For training, it's okay if it takes days or even weeks, but for inference, well, if your user is waiting for an answer from your app, every single millisecond counts. This difference is absolutely critical for choosing the right hardware. And that difference brings us right to the main event, the showdown you've been waiting for: GPU versus TPU. All right, let's meet our competitors. In one corner, you've got the GPU, the graphics processing unit. It was originally made to make video games look pretty, but its parallel design turned out to be, kind of by accident, an absolute genius for AI. And in the other corner, you have the TPU, the tensor processing unit. This is Google's own custom-built chip, designed from the silicon up for one job and one job only, making neural networks go incredibly fast. And if you look under the hood, they're built completely differently. A GPU, like a powerful NVIDIA H100, has thousands of flexible, programmable cores. A TPU, though, it's built around these huge, specialized engines called systolic arrays. And these things are engineered to do one mathematical operation, matrix multiplication, with just brutal, unbelievable efficiency. And this right here, this is probably the single best analogy to understand them. A GPU is like a Swiss Army knife. It's super versatile, good at a whole bunch of different things. A TPU, on the other hand, is a high-performance surgical scalpel. It's designed for one very specific, very precise job. And that right there defines the entire trade-off: flexibility versus pure specialized performance. And you can see how that design choice translates directly into dollars and cents on this chart. I mean, just look at it. The on-demand price per hour for a TPU v5e is just dramatically cheaper than for an H100. And that cost advantage carries all the way through to the metrics that really matter: the cost to serve 1 million tokens for inference, or the cost to train a billion token model. Specialization really pays off on the bill. So this leads us to that classic performance question: are you optimizing for throughput or for latency? TPUs are the absolute kings of throughput. By grouping lots of requests together, they can serve a huge volume of users at a very low cost. GPUs, though, are the latency champions. They can give a single user an answer back with the absolute minimum delay possible, which is essential for anything that feels real-time. Oh, and we have to talk about power, because at data center scale, the power bill is a very big deal. As you can see here, that specialized design makes the TPU incredibly power efficient. A high-end GPU can suck down up to 5 times more power to do the same job. And that's not just an environmental issue, it's a massive ongoing operational cost. But hardware is only half the battle. The GPU's secret weapon and its biggest advantage is its software ecosystem, CUDA. It's been the industry standard for years, and pretty much every machine learning library just works with it right out of the box. TPUs, on the other hand, require your code to play nice with Google's XLA compiler. Now, support in the big frameworks like JAX, PyTorch, and TensorFlow is great, but let's be honest, it can sometimes take a little more work to get everything running perfectly. Okay, so we've laid out all the trade-offs. We've got performance, cost, power, software. So how in the world do you actually make the right choice? Well, it all comes down to one thing: your specific workload. You are going to want to reach for a GPU when what you need most is flexibility. It's perfect for R&D when you're experimenting with brand new ideas or custom code that isn't optimized for a TPU. And if single request, rock-bottom latency is the most important thing in the world to you, think self-driving cars or high-frequency trading, then the GPU is your guy. But if you're playing a different game, TPUs are the undisputed champs of large-scale, cost-sensitive work. If you are training one of these massive, transformer-based large language models, TPUs can save you an enormous amount of money. And for high-volume inference, like powering a chatbot that millions of people use, the TPU's amazing throughput and low cost per query make it the clear winner from an economic standpoint. And hey, don't just take my word for it. This analysis of running the super popular Llama 2 model says it all. For serving tons of users as cheaply as possible, the TPU has a major advantage. But for that raw single request speed, the H100 GPU still leads the pack. But wait, there's another huge factor that's become more and more important, and it has nothing to do with performance or price. The simple question is, can you even get the hardware you want? The absolute explosion in AI has created a modern-day gold rush for high-end GPUs, and that has led to some pretty serious shortages. Companies are sometimes waiting weeks or even months to get access to big clusters of the latest and greatest chips. And this creates a really interesting situation. You see, while those top-of-the-line GPUs are often booked solid, Google's TPUs can actually be easier to get, especially for smaller jobs. And that means for some projects, the best accelerator might just be the one you can actually use today. Okay, so you've weighed the options, you've made your choice. Now for the next big question: how do you actually use it on Google Cloud? Well, Google doesn't just give you one option. They give you a whole menu. And as you can see, the choice really depends on how much control you want to have versus how much you want Google to manage for you. It's a spectrum, from raw virtual machines all the way to fully managed AI platforms. Let's just quickly break down the big three. You can use Google Compute Engine if you want total control. You manage the whole machine yourself. You can use Google Kubernetes Engine if you're running your AI workloads in containers and need to scale them up. Or you can use Vertex AI, which is a fully managed platform that just handles all the infrastructure for you so you can focus only on your model. And this right here shows you the power of that managed world. The Vertex AI dashboard pulls your entire machine learning process, from your data to training your models to deploying them out to the world, all into one single unified place. And look, if you're still not sure where to start, Google literally gives you a flowchart to help you decide. No training data? Use a pre-trained model. Got data but not a lot of coding experience? Try AutoML. If you've got both, you can go all in with custom training on Vertex AI. So really, your whole journey just boils down to these three questions. What are you trying to do? What's the best hardware to do it with? And which service are you going to use to run it?
One last pro tip here on capacity. If you have a mission-critical job, you can use reservations to guarantee you'll have the hardware when you need it. But for jobs that are a bit more flexible, you can use things like GKE's queued provisioning to snag available hardware at a much lower cost. It's a great way to save money.
All right, let's wrap up by looking ahead. Because this whole battle between GPUs and TPUs, it's really just the opening shot in what has become a full-blown hardware arms race. I mean, just look at how fast the TPU has evolved. From the first version that brought training to the cloud, to generations focused on efficiency and cost, and now to the latest chips like Trillium and Ironwood that are delivering insane performance jumps. The pace of innovation here is just staggering. And this is absolutely not just a two-horse race. NVIDIA is constantly pushing forward with new architectures like Blackwell. And at the same time, the other cloud giants, Amazon and Microsoft, are building their own custom AI chips. Everybody wants a piece of this multi-billion-dollar pie. And all of this leaves us with one final fascinating question for the future. As AI models get even crazier and more complex, are we going to see all this hardware converge back to a single, powerful, do-it-all design? Or are we going to see an even bigger explosion of specialized chips with a perfect tool for every single job? The answer to that question is going to define the next decade of AI.